Hi everyone, welcome to the lecture series on structural dynamics. In this class, we will be discussing on the damped free vibration numericals for single degree freedom system. Let us see some numerical on damped free vibration. For example, a question is asked, a mass of 0.907 kg is attached to the end of spring with a stiffness of 7 Newton per centimeter. Determine the critical damping coefficient. Now what we need to do? We need to find out the critical damping coefficient. That means CR, which is 2m omega. Critical damping coefficient is 2m omega, where omega is the frequency, and that can be found out from under root of K by M. K is the stiffness of the spring in Newton per meter. So if I find out the spring stiffness K, which is 700 Newton per meter, because K is given as 7 Newton per centimeter, I convert into 700 Newton per meter, and mass is 0.907 kg, 0.907. So this will give me 27.78 radian per second. Now the CCR, critical damping coefficient, is 2 into mass 0.907 into 27.78, which will give me 50.39 Newton second per meter. So this is critical damping coefficient. I hope you understand this. Fundamentally, we have a relation where C by CCR is a damping ratio. C is absolute damping, C is critical damping coefficient. Where when xi equal to 1, then CCR will become 2m omega, because xi equal to 1. Because we know C by 2m equal to xi omega. This is what we assume during the damped free vibrations derivations of for the response. Okay, so let us look at the next question, which is a damped free vibration record of spring mass dashboard system shows the following data. The amplitude of second cycle, that means x2, is 12 millimeter. Amplitude on third cycle x3 is 10.5 millimeter. Spring constant is given as K is 7850 Newton per meter. Mass of the spring M is given as 2 kg. Determine the damping constant, which is C. C is to be found out. Okay. Now, from the K and M, we can get only the frequency omega, undamped frequency, which is square root of K by M. And for frequency to be radian per second, I must have K in Newton per meter only. If it is in Newton per centimeter or Newton per millimeter, I should change it. So this gives me 7850 by 2 under root will give me the frequency of 62.5 radians per second. Now, when I got a two consecutive amplitude x2 and x3, immediately I should remember the logarithmic decrement definition. The delta logarithmic decrement is ln of x2 by x3. So this gives me ln of 12 by 10.5, so which is equal to 0.133. We also know this is nothing but my 2 pi xi, because this delta value, the logarithmic decrement is so small, definitely the damping ratio will be less than 10%. Then we can directly write 2 pi xi. Otherwise, we should write 2 pi xi by under root of 1 minus xi square. We should write if this delta is sufficiently large. Okay, at this point we not required. So now, so from this relation, the xi is equal to 0.133 by 2 pi, which will be equal to 0.021. That means 2.1% damping. See, very less damping, 2.1% damping. So now what is asked? It is asked to find out the damping coefficient C, and we also know a relation where C by CCR is the xi. So damping ratio already known to me. CCR is 2m omega, then C will become 2m omega xi, where 2 into m is 2 kg, omega is your 62.5, xi is 0.021, which gives me 5.32 Newton second per meter is a damping quotient. I hope you understand. So whenever I need two consecutive or from first amplitude to the n cycle of amplitude, then immediately you should find out the logarithmic difference. From their damping ratio, from their damping coefficient can be found out. Let us go to the next numerical. A mass of 1 kg is to be supported by a spring having stiffness of K equal to 9800 Newton per meter. So I need not to convert. The damping coefficient is 5.9. That means C is given to me 5.9 Newton second per meter. Determine the frequency of the system. That means since damping is there, the damped frequency is what I need to find out. Okay. So now the damped frequency can be found out depending upon the damping. So if we, right now I don't know how much is the damping present. Okay. So what we'll find out, that how much is my damping ratio. So first I should find out how much is the damping ratio. So for that, first I can also find out the mass is given, the m is 1 kg. So I can find out the undamped natural frequency, which is root over k by m, which is equal to 9800 by 1, which gives me 31.3 radian per second. Now I need to find out the xi damping ratio, which is C by 2m omega, because C by CCR is damping ratio. So C is given to me, which is 5.9 by 2 into 1 into omega, which is 31.3, gives me 0.094. That means in terms of percentage, 9.4%. That means damping is very less. So I can directly, I will say that omega d is very close to omega, right? So that is nothing but my 31.3 radians per second. This is damped or undamped. Same, because damping ratio is very less. Still, or if you want, we can find out omega d is omega into under root of 1 minus xi square, where 31.3 into 1 minus 0.094 square. So what we get is 31.2 radians per second. Not much difference. Okay. Now next question is, part of the question is find the logarithmic decrement. That means I need to find out the delta. I also know the relation between the damping ratio and logarithm decrement. Delta is 2 pi xi. Xi is already known to me. I can very well find out 2 into pi into xi 0.094, which is equal to 0.59. And also find amplitude of 3 cycles if the initial displacement is 0.3. That means after 3 cycles, that means n equal to 3, the initial amplitude is 0.3. So the third cycle amplitude is to be found out. That means the delta equal to 1 by 3 ln of x0 by or x1 by x3, which is 1/3 of ln of x0 is given as 0.3 centimeter by x3 is to be found out, third amplitude need to be found out, which is equal to the delta which already found out 0.59. So from that what we get, the ln of 0.3 by x3 will give me 3 into 0.39, which is 1.77. Then 0.3 by x3, can write here, 0.3 by x3 is equal to e to the power of 1.77. From there x3 can be taken as 0.05 centimeter. This is how I should find out the displacements after 3 cycles. So let us look at next example. A mass of 20 kg is suspended from the spring of stiffness 39240 Newton per meter. A dash part is fitted and it is found that the amplitude of vibration diminished from its initial value of 25 mm to 6.25 mm in 2 complete oscillations. Find the resistance offered by the dash part at a velocity of 0.3 meter per second and the frequency of damped vibration. This is asking to find out frequency of damped vibration and the resistance offered by the dash part. We call it as FD. Okay. Compare this value with the frequency of free vibration. So what is to be found out here? Simply FD. That means what? C into velocity. Okay. So first the C is to be found out, damping coefficient. Velocity is given as 0.3 meter per second. Then we need to find out frequency of damped vibration, which is omega d, which is omega into under root of 1 minus xi square. So before finding the resistance offered by the dash part FD, I need to get the C, I need to get the xi and then omega. Very simple. So very simple. Now what we get, since 2 amplitudes are given, 25 and 6.25 in 2 complete oscillations, so the logarithm decrement delta is half of, means 1 by 2 cycles, ln of 25 by 6.25. So this gives me 0.693. So once I know the logarithm decrement delta, which is also equal to 2 pi xi by under root of 1 minus xi square. Of course, I can very well neglect this term thinking the neglect this, make it to the 1 because this is still less, but still if you want you can calculate. So if you neglect this, if you neglect this, considering the delta is small, so directly the xi is 0.693 by 2 pi, which is 0.11. That means 11%. Okay, or 11%. If you consider the denominator term also, what you may get it 0.109, some 89, which is also closer to 10.89 is closer to 11%. So once I get a xi, so now still I need to get a c there. So c is equal to 2m omega xi. So 2 into m is 20 kg and omega I need to find out. The omega can be found out. Omega is under root of k by m, which is k is 39240 Newton per meter. I need not to change units, by 20 kg, which I can get omega as 44.3 radians per second. So now I can use two into 44.3 into xi, which is 0.11. So I will get 194.9 Newton second per meter is damping coefficient. But what is it asked? It is asked to find out the resistance offered. That means your FD equal to C, which is 194.9 into x dash. X dot is a velocity that is given as 0.3, which gives me 58.46 Newton. Right? Now is asking frequency at the of damped vibration, which is omega d, is omega into under root of 1 minus xi square, is omega is a undamped frequency, which is 44.3 under root of 1 minus 0.11 square will give me, it gives me 44.03 radians per second. So very less difference between the damped vibrations and damped frequency to the undamped frequency. This is how we solve a problem. So let us look at the next problem. A machine of 20 kg. A machine of 20 kg, that means mass equal to 20 kg, is mounted on a spring and dashboard. That means damped vibrations. C is there. The total spring stiffness K is 10 Newton per millimeter, but I must convert into Newton per meter immediately. So 10 into 1000. So 10,000 Newton per meter. And the total damping which is C is 0.15 Newton per millimeter per second. So I want to be in Newton per meter, Newton second per meter. So into 1000 gives me Newton second per meter, which is equal to 150 Newton second per meter. Now once I know this data, asking to find out the displacement and velocity of mass as a function of time. That means it's asking to find out the x of t and velocity x dot of t. What else is given here? If the system is initially at rest, that means x at t equal to 0, which is x naught equal to 0, and the velocity, which is u naught, is equal to, also called x dot of t equal to 0, is equal to 100 millimeter per second. With this initial condition, I should be able to find out the displacement and velocity as a function of time. Then once you get that, the second part question is same displacement and velocity at time equal to 1 second. Just substitute t equal to 1, we get that. So now look at the question. So now I need to find out the omega, which is square root of k by m. K is 10,000 by 20. So I get 22.36 radians per second is the undamped frequency. So now if I assume the x of t as e power minus xi omega nt into a amplitude into the cost omega t minus phi. If this is my response, assumed response, substituting the initial conditions, this is the first initial condition, which is second initial conditions. From first initial conditions, so this becomes 0 when t equals 0. T0 means this is 1 rho. T0 means cos of minus phi is cos phi. So since rho cannot be 0, so cos phi has to be 0. When cos phi 0, that means phi equal to 90 degrees. At phi 90, cos phi is 0. So this we obtained phi. Now I have to obtain the rho. From the second condition, initial displacement. What is initial initial velocity is 100 millimeter per second. So differentiating this one more time, what I get, x dot of t is equal to e power minus xi omega nt. Differentiating this e power nt, will have minus xi omega n into second function as it is cos of omega t minus phi, and rho will be there anyway, so we will keep rho outside, plus second function, differentiation of second function. The first function I have to write as it is, so minus e power minus xi omega nt into second function differentiation is minus sine. So minus of sine omega t minus 5 into omega. So I can take this as a minus omega. Okay. Now if I substitute this, the left hand side, which is equal to the 100 millimeter per second, is the rho is anyway common. We need to even e to the power of minus xi omega nt can also be taken as common, and substituting cos phi t equal to 0, when t equal to 0, this will become minus xi omega n cos phi minus omega minus of minus become plus sin phi. Now since anyway cos phi is 0, that means this term is 0. When phi equal to 90 degrees, this term, this sin phi will be 1, and this term will be equal to 1 because t equal to 0. So what I left with is omega into rho is 100. So the rho is equal to 100 by omega. Omega anyway I found out is 22.36. So the rho will be 4. This amplitude of vibration 4.47 millimeter because velocity millimeter per second. So once I found out this rho, I need to find out the damping ratio for this. So the damping ratio xi is c by 2m omega, which is c is given as 150 by 2 into 20 m. Omega is 22.36, which is nothing but 0.167. That means approximately 16.7%, more than 10%. You can also find out xi omega multiplying these two quantity, because everywhere r omega n doesn't matter. So 0.167 into 22.36 will be approximately 3.7. Now substituting into the response, which is x of t as e to the power of minus xi omega nt, means minus 3.7t into rho we got it as amplitude got 4.47 into cos of 4.47 cos of omega t. Omega is 22.36 t minus 5, which is pi by 2. So pi by 2 means we will get a sine. So 4.47 e to the power of minus 3.7 t into sine of 22.3 t. This is the response at time t equal to 0. This is a x of t. So this is a one part of the solution. When we differentiate this one more time, so I'll get a velocity x dot of t. When we differentiate this, you get a velocity. So same one, this differentiation of this function into this function plus this function into differentiation of second function. So like this, if I do e to the power of minus, of course the coefficient 4.47 and e to the power of minus 3.7 t also will be taken, can come as a common. So 22.3 into cos of 22.3 t, right? Differentiation of second function. First function anyway multiplied, taken a common. Then plus e to the power of differentiation of the second, this first term will be minus 3.7 times into e to the power of minus that taken a common, then sine of 22.3 t. So that minus will be here. Then it looks like the form of cos A cos B minus sin A sin B, converting that in terms of sin and cos. So I know how to convert that. I can say that I'm thinking this to be a cos A. That means this 22.3 is this base, and this sine, that means 3.7. So I can get this as 22.6. So this will be my some phi, another angle, or you can say cos some A, you can say A. So I will have, then I have to divide and multiply with the 22.6 everywhere, and then division comes here. So 4.47 into 22.6 and dividing e power minus 3.7 t 22.3 by 22.6 into cos 22.3 t minus 3.7 by 22.6 sine of 22.3 t. Now this is 22.3 by 22.6 is cos A. Cos A, cos B minus sin A, sin B. So cos of A plus B. So multiplying this and this, we get 101 into e power minus 3.7t into cos of 22.3t plus the A. So the A is nothing but tan inverse 3.7 by 22.3. That's all. X dot of t. By substituting t equal to 1 second, so I can find the value of this. T is equal to 1 second, I can get the constant value. Thank you.